Hello, everybody. I'm back. I don't think you expected me not to be back. But say hello in the chat. Let me see who's here. I always like to see an active chat. Keeps me entertained. Whoever that was that hits the like button the second the video starts, you're the star of the class. Sarah, Lauren, good to see you. 4 upvotes. Jax, Jared, warming up the chat. I like to see that. We need a good high Friday energy. That's what we need. Oh, no. James says thanks. Addie, hello. Navi, back for a linear and then calculus, correct? Ellie, hey. Jack, hello, welcome to the chat. Rena, hi. Molly, had to tune in for this lecture. She must have seen the viral video. James, just brewed some coffee. Saritha, hey. Good to see you, good to see you. Okay, so before we get started, show of hands. Who watched the video? Who watched the video that I sent you all last night? And was it epic or what? Rena says, I did with no enthusiasm whatsoever. Oh, just kidding. The best video I've ever seen. That's enthusiasm. Will knows. It was epic. Yeah, Ellie, you're right. Deserves to go viral. Lauren, lots of special effects. That's fair to say. Okay, well, if you haven't watched that video yet, it's the best video I'll ever make. It's not really that good, but it's the best I'll ever make because I don't have that much producing skills. Okay, well, we should probably get started. Yeah, Jax, great point. How is it not viral? Michael Bay could never. Well, feel free to continue to talk about this in the chat, but we should get started with the simultaneous sip. And, we should go over the material that video was inspired by. Right, so it's not just like on a test, you're going to be screaming about the domain and intercepts and all that stuff like I did in the video. You'll actually have to figure out what those are and apply them to curve sketching. Okay, so this is section 3.5. 3.6 is basically the same thing. So we're not going to actually have a section named 3.6, but the WebAssign 3.6 homework is from the material in this section. It's summary of curve sketching. So we're gonna have 7 facts that are needed to graph a function by hand. Okay, so that's going to be the idea. Hello, Max. Good to see you. So the following is a checklist, and so when we do these curve sketching problems, we're gonna have to go one at a time. Bing, 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 all the way through until we get all 7, and then we can put it together for a graph. So the following is a checklist of information. To sketch the graph of a function by hand. Looks like we only had 2 participants in the simultaneous SIP today. That's fine. Fridays tend to have low participation for those. Okay, so the following is a checklist needed to sketch a function by hand. Typically, in a normal class, I would provide this checklist to you on the exam. But since you'll have open notes, I'm not going to provide it to you, or maybe I will, but so you should write this down because each of these curve sketching problems, I want you to go through each of these steps. Oh, good. So maybe there's a little bit of delay with the SIPs. Okay, so the first thing is the domain. Okay, so when we graph our function, the graph should only be above or below the x values that we're actually allowed to plug into our function. All right, so we're going to have to check, make sure we don't divide by 0, make sure we don't take the square root of a negative number, all the things that we have to avoid. That's how we'll start our question. The second part is the x-intercepts. The y-intercepts. So again, this is just something that you knew how to do from pre-calc. X-intercepts, you would set our function equal to 0 and solve for the x values. And the y-intercept, you just plug in x equals 0 and see what pops out. Okay, so far there's nothing new here. Okay, the next one is symmetry. So my question for the chat is, how do you test, before I write that out, how do you test if a function is even or odd? Okay, what was our way to check that? Yeah, exactly. So remember, even means that f of negative x is equal to f of x, and odd means that f of negative x is equal to negative f of x. Yeah, Max, what it's going to look like is exactly that. So if it's even, it's symmetric about the y-axis. If it's odd, it's symmetric about the origin. So you might have to look back in your notes to remember some of these facts, because this will help us graph the function. Periodic is when we have trig functions involved. Okay, so we'll have to deal with those separately. So D. Again, so this isn't really calculus related, right? This is still pre-calc. Maybe you didn't define these in your pre-calc class, but there's no derivatives or anything involved yet, or limits. So D is the asymptotes. So we want to find vertical asymptotes, horizontal asymptotes. And then the last one, which we haven't talked about yet, are slant asymptotes. So this is coming soon. Okay, so we're going to have to find all the asymptotes, horizontal asymptotes, vertical asymptotes, or slant asymptotes. Horizontal and slant, you could either have one or the other, or neither. So we'll check for those. Okay, next, this is when we finally start getting to some derivatives. Intervals of increase or decrease. So how do we find, so just type in the chat, how do we find when our function is increasing or when our function is decreasing? Yeah, exactly, Max. So this part E is when we first take our derivative. We're going to take our derivative, check when it's positive, and check when it's negative. Yeah, Isabella, that's also right. So we'll take the derivative, set it equal to 0, and then we'll use test points on the number line. And that's how we check if it's positive or negative. Okay, so we finally take our derivative at part E. Part F is local max and local min. So we want to find when our function goes from increasing to decreasing or decreasing to increasing. And that will give us the local max and local mins, right? And these we're going to represent these as points. So there'll be points on our graph. So again, so we took a derivative before E, and then we've used that information for E and F, and then G is concavity and points of inflection. So how do we find the concavity and points of inflection? Yeah, Jared, you're right. We take the second derivative. So we'll take another derivative here, and we're going to have to, we'll repeat the same process as before. We'll find when, yeah, the second derivative is positive or the second derivative is negative. Jack said, be careful there. The second derivative test actually tells us, it does tell us about the concavity, but we use it for local max or local mins. So I think what you're saying is, I think what you mean to say is that we look at the second derivative, but the second derivative test is slightly different. That would be for F. Okay, and then so what we'll do is we'll get all of this information, A, B, C, D, E, F, G, and then we're just going to put it all together and see what the graph looks like. And that's how we sketch a graph by hand. So let's take a look at an example. And before we get to this example, let me make a promise to you all that I have to keep because it's on video and it's being recorded. Tonight, before midnight, Eastern Standard Time. You know what? West Coast time. So give me a few extra hours. I will post practice problems for next week's test. Okay. So if you check Canvas, let's say Eastern. If you check Canvas and it's not up by tonight, just email me and say you promised us some practice problems. But they're already written up, so I'll just try to post them right after class. Okay, and then next week we should still have at least a day, hopefully a little bit more, to just review for the test. Okay. So the example is sketch the curve of the function y equals 2x squared over x squared minus 1. Okay, and unfortunately, I don't have enough space in my whiteboard to be able to write out all of these 7 things at once. So, you're going to have to make sure you keep up with what I'm writing, so you have it in your notes, because at some points I'll have to erase it. I mean, I guess I do have this whiteboard we could use also if we don't want to erase things. We'll figure it out when we get to that point. Okay, so let's start with part A. The domain. How do we find the domain of this function? You could either type in what the domain is or just tell us the process for finding it. Okay, all numbers except for 1. What about -1 as well? Yeah, so what we're going to do is so our domain here, we have a rational function. We can't divide by 0. So we'll take our denominator and say that it's not equal to 0. And then we could factor this. And so we have x is not equal to plus or minus 1. Okay, and we don't need to be, I see a lot of you are using interval notation. That's great. I'm not going to mark you off for whatever notation you want to use, but we just got to just keep in mind, we're allowed to plug in any x value except for 1 or -1. Okay, because really it's the details at the end that we're going to be looking at. So if you could take this and apply it to our drawing, that's what matters. Okay. For B, we want to find, we'll start with, let's start with vertical asymptotes because that's what we did earlier in the semester. And so what do we have to do to find the vertical asymptotes? Uh-oh, I've lost my connection to chat. Okay, you guys think about this. I'm going to get my iPad to see if I can watch the stream along with you guys. Yeah, I got no check here. Let's see. Okay, can somebody type something into the chat to see if it shows up on my iPad? Okay, great. It shows up on the iPad. This is frustrating, but we'll make it work. All right, so we want to find the vertical asymptotes. We want to take the limit as x goes to each of these numbers from both the left and the right to see if our graph is going upwards or downwards from each direction. Okay, so we'll take the limit as x goes to -1 from the left of our function. Okay, and so we're going to be plugging in a number that's close to -1, but a little bit smaller than it. And our numerator will be positive, and our denominator will be a negative number, right? Because we're going to be plugging in a number that's a little bit more negative than -1, so like -1.1. So we'll have a small negative number in our denominator, and we'll have a positive number in our numerator. So this goes off to -infinity. Oh, sorry. Okay. I was looking at the wrong thing. D. That's okay. Ignore the last 5 minutes of this whole confusion. That's for asymptotes. We got to do x and y intercepts first. Sorry. Okay. I saw this down here, and I thought this was the second thing. Really, the second thing is up here. X intercepts. Okay, these are easier. So the x-intercept, we want to just set our function equal to 0 and solve. Okay, when does this happen? It happens when our numerator is equal to 0. So we have the point 0, 0 as our x-intercepts. So for the y-intercept, we just plug in x equals 0 and see what happens. We already know it's going to be the point 0, 0, but let's just go through the process anyway. So it reduces to 0. Our y-intercept is the point 0, 0. Okay, sorry. Let's get to symmetry now. So let's take a look at f of negative x. So we have 2 times negative x squared over negative x squared minus 1. Well, negative x squared is just x squared. So this is 2x squared over x squared minus 1, which is the same thing as f of x. So we're even, which means we're symmetric about the y-axis. Okay, and feel free to, if I'm going too fast, just put a comment in the chat. I'm still able to follow the chat along in my iPad, luckily. Okay, so since we know it's even, we don't have to check if it's odd. I mean, that would have been the same process. Okay, D is the asymptotes. So let's start with vertical asymptote. This is what I was going on about earlier. So we want to take the limit as x goes to -1 from the left. We want the limit as x goes to -1 from the right of our functions. The limit as x goes to +1 from the left. And the limit as x goes to +1 from the right. Okay, because this will tell us if our curve goes up the asymptote or down towards the asymptote. Okay, and so I'm not going to go through all the steps of how to evaluate these limits again, but I would recommend looking back in your notes for how we did this at the beginning of the semester. It'll come back to you with a little bit of practice. But here, so what we're doing is we're plugging in a number that's really close to -1, but a little bit larger, a little bit more negative. So our numerator is going to be positive. Our denominator is going to be a really small negative number. So we have -infinity. Like -0.9, for instance. Oh, sorry. Let's try this again. Our numerator is positive. Our denominator, we're taking a number that's a little bit further to the left on the number line than -1, like -1.1. This denominator is also a small positive number. So we're going to get positive infinity. So sorry if there is confusion there. Here we're taking a number that's a little bit close to the right of -1 on the number line. So like -0.9. Our denominator will be negative. Our numerator was always going to be positive. So we have -infinity. Similarly, here we're taking a number a little bit to the left of 1 on the number line. So like 0.9. We'll have a positive over a small negative number. -infinity. And here, it's going to work out to positive infinity. Okay, so those are our vertical asymptotes. And we'll be able to see this when we look at what our graph looks like using the concavity and the increase and decrease. These are going to go hand in hand. So it's a good way to check. We'll see how we could check our answer at the end. Okay, so we're still on D, which is horizontal asymptotes. So we want to remember to find a horizontal asymptote, and this is something you should remember for 15 minutes from now when we're taking the quiz. Take the limit as x goes to positive infinity of our function. And we want to take the limit as x goes to negative infinity. Okay, and so we might need a little bit more space. So to evaluate this limit, remember we multiply the numerator and denominator by 1 over x raised to the highest power that appears in the denominator, which is x squared. So we have the limit as x goes to infinity of 2 over 1 minus 1 over x squared, which is equal to 2. Right, because this term goes to 0, so we're just left with 2. All right, now we'll do the same thing, the limit as x goes to negative infinity. We're going to go through the same exact algebra here. So our horizontal asymptote is y equals 2. And we just have one horizontal asymptote. Jared asks, in this scenario, could you use the shortcut? Sure, you could use the shortcut in this situation, where you just divide the coefficients. Okay, but I'd be careful because, maybe I give a harder question where that trick doesn't work. You should be prepared you should be prepared to evaluate these limits if the shortcut doesn't apply. But here, yeah, you could just use the shortcut because I know there's a lot of steps here. Yeah, really E, F, and G are the ones where I want you to be careful and really go through the steps with a lot of precision. That being said, we should maybe start with E. So we need the derivative, right? To find when our function is increasing or decreasing, that requires the derivative. So we want to take the derivative of a quotient. And so that's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay, so we have f prime of x. This simplifies to minus 4x over x squared minus 1 squared. And so the question is, what do we do with this derivative now? Like, what should we do? We found the derivative, but how does that tell us about if it's increasing or decreasing? Right, so we'll set it equal to 0, but what else do we have to check? Yeah, Addie, you're right. So we want to find the critical numbers, which means we set it equal to 0, or we find, which I worked at. Sorry, I'm trying to say too many things at once. We want to find when our derivative is 0 or undefined. Okay, and so, and we have to include the fact that, well, it'll appear from the derivative, but we can't be looking at values that aren't in our domain either. Yeah, so when our derivative is equal to 0, that means the numerator is 0. And so in this case, x equals 0. When our derivative doesn't exist, that implies that the denominator is equal to 0. Or x is plus or minus 1. Okay, so we'll take our number line. We'll take our number line, and we'll take a test value in each of these segments. And check, is our derivative positive or negative in each of those segments? Okay, so when we plug these into our derivative, look at the denominator. The denominator is always going to be non-negative, 0 or positive. So we just have to look at what happens when we plug it into the numerator. So we get a positive, a negative, and a negative. So our function is increasing, increasing, decreasing, decreasing. So that's E. What about F? Are there any local max or local mins? Yep, Isabella, you're right. Local max at 0, 0, right? Because our function goes from increasing to decreasing there. And there's no local mins. Okay, and so now we're on to the final step before we get to graphing. Which is the second derivative. Okay, so we want to get the second derivative of this function. So let's do the quotient rule again. So bottom times the derivative of the top minus the top times the derivative of the bottom, which is 2x squared minus 1 times the derivative of the inside, all over x squared minus 1 squared squared. Okay, and so I'm going to just tell you what this simplifies to, but you should try this on your own. So it simplifies to this. And now we're going to do the same exact thing as we did with the first derivative, but with the second derivative. Find when it's equal to 0, find where it doesn't exist, and then check if it's positive or negative, and that will tell us about the concavity. So when f double prime equals 0, that means our numerator is equal to 0, but 12x squared plus 4 never equals 0. So there's no zeros here, but we can check when it doesn't exist. So we have plus or minus 1, again, as when our second derivative doesn't exist. Okay, and so now our test values, which we'll plug into our second derivative, be -2, 0, and 2. When you plug in -2, you have a positive divided by a positive. That's a positive, so we're concave up. You plug in 0, you get a positive over a negative. That's a negative. Concave down, and then last we have concave up. So here's my question. Are there any points of inflection? And well, so Rena, you guessed what I expected somebody would guess. You would think that -1 and 1 would be points of inflection, or there would be points of inflection at those x values. But we got to remember these x values have to be in our domain, right? And -1 and 1 lie outside of our domain. So there's actually no points of inflection here. Okay, so before we go to graphing, let's just take the information we had from part E and part G and put it all together. So we'll take a third number line and we'll break it up at every value. We've broken up the number line along the way. So here it's -1, 0, and 1. And we'll just check for the concavity and the increasing or decreasing. So between -infinity and -1, our function is increasing and concave up. It looks like this. Between -1 and 0, increasing and concave down. Increasing and concave down. Looks like this. Between 0 and 1, decreasing and concave down. And between 1 and infinity, we're decreasing and concave up. Okay, let me quickly put this together. Oh, you have an hour to do this quiz, so maybe it's okay if I take my time to finish this. So let's put it all together. We had vertical asymptotes. We have our x and y intercept. We had a horizontal asymptote. And we have the symmetry that it's even, so we should make sure that our picture is symmetric about the y-axis at the end. But now let's just put it all together. We know it goes off to this horizontal asymptote, and it's we also said it goes up to infinity here, so we could connect the dots this way. Here, we're down here, and we put it all together like this. Okay, and then we could mark some of our important points like the origin. Yeah, but this is the basics of curve sketching. Obviously, we're going to do another example on Tuesday. Let me write out the next example so you could try it on your own this weekend, and then that's what we'll do on Tuesday. Okay, well, yeah, so this is sketch y equals x squared over the square root of x plus 1. So your quiz is posted to Canvas. So you'll have an hour, but it should only take you about 10 minutes. Write it out on a piece of paper and try to upload it to me as a PDF. Yeah, let me and email me if you have any issues with this technology. I know it's tough for everybody. But yeah, I'll stay here for a few more minutes answering questions on the chat. But if not, have a good weekend. Make sure you follow the rules. You know, if you need to see your friends, just see them on FaceTime or Zoom. It's really not that big of a deal. Be responsible. I don't know what else to say. But make sure hit the like button on your way out. It really helps. Before you know it, we'll hit 1,000 subscribers. Okay, have a good weekend. Ioannis asks where to find the quiz. It's on Canvas. Hopefully it's showing up there. Has anybody found it on Canvas? Try to submit it as a PDF because it's easier to grade because the TA will just write on it with their stylus. And PDFs are easier to work with. All right, yeah, it looks like some people have found it on Canvas. Yeah, try to do it as a PDF. Email me if you're having trouble. There's a few free apps. Adobe Scan, I know, is one of them that allows you to do it. But yeah. Okay, if not, if there's no more questions, I'm gonna end the stream right now. So bye-bye.